Rotational motion and angular momentum. Have you ever wondered why a figure skater spins faster as she pulls her arms in? Or maybe why tornadoes seem to rotate with such power? Well, then look no further, as these are examples of rotational motion. It's similar to linear motion, but instead of moving in straight lines, such as running or walking, objects in rotational motion spin around an axis. Examples include the Earth spinning on its own axis to maybe a simple spinning top. Their concepts are very similar, just with differentiating components. While linear motion may use speed or velocity, rotational motion uses angular velocity. In a similar way, distance is to linear motion as angular displacement is to rotational motion. Whereas linear motion uses mass, rotational motion uses something known as moment of inertia, which is something we'll discuss later. Lastly, there is a difference in acceleration and in angular acceleration. A key concept when discussing rotational motion is a phenomenon known as angular momentum. But what exactly is it? To understand it, we have to understand what momentum actually is, or more specifically, linear momentum. It is best defined as the product of the mass and the velocity of an object. Let it be known that any moving object with a mass possesses momentum. The only difference in angular momentum is that it deals with rotating or spinning objects. It's important to note here that an increase in mass or an increase in velocity will result in a higher momentum. So in this case, while Tom is chasing Jerry, while they both are seemingly going the same velocity, Tom has a higher mass than Jerry, so it's safe to assume that Tom has a higher momentum, even though they are going the same speed. So let's kind of tie this back into angular momentum, which can essentially be called the rotational equivalent of linear momentum. It describes the quantity of motion an object has while it is rotating on its axis, or it can be better described as the product of a moment of inertia and angular velocity. The equation therefore goes like this. Angular momentum is the moment of inertia times angular velocity, which is the rate at which an object rotates. This is something that ice skaters tend to go through naturally as they are spinning in a circle. However, let's kind of define what a moment of inertia technically is. By definition, it is the resistance of an object to changes in its rotational motion. There are two main factors that it is dependent on, one being the mass of the object, and two, how that mass is distributed relative to the axis of rotation. It can be further broken down into this equation, where it is the sum of the match of each point and the distance from each point from the axis of rotation squared for all the point masses of which it is composed. Essentially, the more mass is concentrated farther from the axis, the higher the moment of inertia, into which the harder it is to spin. So let's go ahead and take a look at this from an ice skating perspective. As seen here, as an ice skater spins with their arms extended, the mass of the skater is spread out farther from the axis of rotation, which means that they have a higher moment of inertia, make it harder for them to spin quickly. In contrast, when an ice skater pulls their arms closer to the body, the mass is concentrated closer to the axis of rotation, which means there is a decrease in moment of inertia, and the skater can spin faster. Continuing, let's follow up with what angular velocity is, which essentially is the rate at which an object rotates, measured in radians per second. However, there's something super important that we need to take note of. That is the law of conservation of angular momentum, which states that in a closed system with no external torque acting on it, angular momentum is conserved. This means that the initial total angular momentum is equal to the final total angular momentum when no torque is acting on it. But what exactly is torque? To understand what torque is, we have to understand what it does, essentially. In all, torque is a force that changes an object's angular momentum, much like a force that changes linear momentum. It can be broken down into this formula, which is denoted as torque is equal to the change in angular momentum over the change in time. It essentially states that torque is the rate of change of angular momentum with respect to time. If you apply a torque to an object, you are changing its angular momentum, and the amount of torque applied determines how quickly the angular momentum changes over time. Lastly, we're going to talk about rotational kinetic energy, which is essentially the energy an object has due to its rotational motion. And it is shown in this equation, which is 1/2 of the moment of inertia times the angular velocity squared. For an ice skater, this energy is associated with how fast they spin or rotate on ice. For example, when a skater spreads their arms, it increases their moment of inertia, which in turn decreases their angular velocity, in which they slow their spin, which decreases their rotational kinetic energy. Alternatively, when a skater tucks their arms closer to the body, they decrease their moment of inertia, their angular velocity increases, causing them to spin faster and gain more rotational kinetic energy. Now, using everything that we've learned, let's try and solve a problem together. As ice skating has been the hot topic of today's presentation, I think it's only fair that we do an ice skating problem. So let's suppose an ice skater is spinning at 0.6 revolutions per second with her arms extended. She has a moment of inertia of 1.75 kilograms per meter squared with her arms extended and of 0.45 kilograms per meter squared with her arms close to her body. Firstly, what is her angular velocity in revolutions per second after she pulls in her arms? And what is her rotational kinetic energy before and after she does this? So let's start with part A. So in this specific problem, we are looking for the skater's final angular velocity, which in this case is how quickly she rotates around her axis after pulling her arms in. Because there is no external torque activity on the system, the conservation of angular momentum applies. So the initial angular momentum is equal to the final angular momentum, and which it can be broken down further, where I and omega are the initial moment of inertia and angular velocity, and I and omega are the final moment of inertia and angular velocity after the dancer pulls her arms in. So since we are looking for the final angular velocity, let's rearrange the equation. By dividing the final moment of inertia to the other side, we finally end up with this equation. So we can substitute the given values that were provided to us, simplify it down, and end up with 2.33 revolutions per second. And finally, let's determine her rotational kinetic energy before and after she brings her arms in. And for this problem, we will use the formula for rotational kinetic energy, which is 1/2 moment of inertia times angular velocity squared. So let's start off with before she brings her arms in which her arms are extended. With the provided information, we can determine that her moment of inertia is 1.75 kilograms per meter squared, and her angular velocity is 0.6 revolutions per second. However, we do need the angular velocity to be in radians per second, so let's go ahead and convert that by multiplying it by 2 pi radians. After getting 3.77 radians per second, we can go ahead and input that into our equation. Simplify that down, simplify that down, and end up with 12.43 joules, which is her rotational kinetic energy as her arms are extended and not brought into her body. Now let's go ahead and determine her rotational kinetic energy once she brings her arms in. From the given information and what we determined through part A, our moment of inertia is 0.45 kilograms per meter squared, and our angular velocity is 2.33 revolutions per second. Once again, we do need to convert the angular velocity to radians per second, which we do by multiplying it by 2 pi radians, into which we get 14.6 radians per second, to which we input into the equation, to which we simplify that down, to which and end up determining that her final rotational kinetic energy as she brings her arms in is 53.3 joules. So let's take a step back and kind of reflect on what we just talked about. During this time, we discussed angular momentum, law of conservation of angular momentum, moments of inertia along with angular velocity, torque, rotational kinetic energy, and rotational motion, as well as we solved a ice skating problem. Hopefully next time that you go to an ice skating rink and you see somebody doing all these tricks and these twirls and spins, you kind of reflect and see what is actually happening physics wise with their angular momentum and their rotational motion. Here are our citations for the references that we used. Thank you.